Hello and welcome to Unsupervised Thinking, a podcast about neuroscience, artificial intelligence, and science more broadly. We are a group of people who study computational neuroscience. I'm Grace.
I'm Josh.
And I'm Connor.
And the topic for this episode is Bayesian just so stories. It comes from a series of articles that we read, the idea being that some of the modeling used in neuroscience is kind of perhaps not as useful as some people are claiming it to be, and there was a controversy about this type of modeling work and its role in psychology and neuroscience. So we read this series of articles that started with one called Bayesian Just So Stories in Psychology and Neuroscience by Jeff Bowers and Colin Davis, and that was in 2012. And the next two articles that we read were first a group of people who were responding to this first article, and then after that, the authors of the original article responded back. And so this is just like a little thread that happened in the research community around the topic of Bayesian modeling in psychology and neuroscience. So we should start by explaining, I guess, what Bayesian models are and how they're used in psychology and neuroscience, and then we can get into what exactly was being said in these articles.
So I guess to elaborate slightly, the idea is that in psychology and neuroscience, you want to come up with theories that explain, in psychology, it's usually human behavior, usually in some kind of controlled often in some kind of controlled experiment, which could be like a perceptual experiment or a decision-making type of experiment. So people are performing some kind of task. And in neuroscience, you want to explain the behavior of neurons in the brain, maybe, some measurement of the activity of neurons. So it could be in animals, or it could be in humans if using like fMRI or EEG or MEG or these kinds of things. And so there's there's this sort of maybe you could call it like a modeling framework, which is the term that someone uses in one of these papers, which is kind of Bayesian. And maybe we should explain just broadly what Bayesian means for people who don't understand. Someone want to do that?
Sure. So, there are many different perspectives on this, and people argue about, Bayesian probability and Bayesian statistics from a sort of philosophical perspective. But I think the simplest way to think about it, certainly like as a general introduction, is just there's probability, which is like how we compute the relative probabilities of things. And so there's like a whole branch of, let's say, math around how do you manipulate probabilities in the right way. So just like there's calculus or linear algebra, which are subfields of math for how to manipulate certain kinds of mathematical concepts. Probability has an associated field of math with it. And if you are interested in doing certain kinds of computations with probabilities having to do with real data, essentially the standard mathematical framework for treating that is going to be Bayesian probability. Basically, if you want to do modeling where the models talk about probabilistic quantities, kind of the agreement is if there's an interaction between these sort of probabilistic quantities and data, then it's going to be Bayesian modeling. So we can try to give like a concrete example of this.
Yeah, I think the like words, well, okay, I guess you were using words, but you're using a lot of math words, some of these real words. The words way to describe this would be something like a Bayesian approach gives you a way to combine different sorts of information in a messy world.
Yes, that's a good way of describing.
So
if like you have noisy data, if there's if you have uncertainty about certain quantities and you have noisy data, the right way to combine those pieces of information is using Bayesian computational tools.
And an example that comes from the first article in this series is if you are, this was written by an academic and for an audience of academics, so they say if you're walking around campus and you see someone from afar and you have some kind of perceptual evidence, you're seeing this person, but they're not close up to you, so there's some, uncertainty. You think it might be someone that you know. You might combine this kind of visual information that you're getting in this moment that you see someone who kind of looks like someone that you know with the knowledge that you have about how likely it is that that person would be on the campus. So if it's a fellow professor or a student, it seems very likely that they might be on the campus, and you think that this person looks like them, so you might kind of strongly conclude that that is them. If it's someone that you knew from high school or, your grandmother or something like that, someone who's unlikely to be on the campus, even though you're getting kind of a visual stimulus at the time that says that this person looks like that person you know.
Only vaguely. Yeah.
Yeah, you're getting some small amount of input that says maybe this person kind of looks like someone I know. Your prior information about how likely it is for them to be there might make you conclude, but that's not them. And so this is the way in which Bayesian theories can enter into models of perception and decision making. It's a core concept is the idea that you're going to combine prior information that you have with current information that you're getting.
And it doesn't have to be just one combination, right? To be clear, I mean that's like the right way of introducing it, as like there's one combination, there's some prior knowledge, and then there's some data that you get that's noisy, and you update your prior belief. But like, kind of very complicated things can get bundled into this framework of computation, right? So like, you could have some prior knowledge, and then you see many different pieces of data, and you combine all of those pieces of data, or the prior that you have could be very weak and non-informative, and you could just get many different pieces of data. And as long as you have kind of credibility associated with each piece of data that you get, like how uncertain was each piece of data, then there's sort of a calculus for how to optimally combine the different pieces of information weighted by their uncertainty.
Yeah, and like another thing would be that we're kind of implicitly talking right now about, say, combining, in Grace's example, combining a piece of information about perceptual information about the identity of a person with prior expectations over who in a given context you might expect to see, and kind of combining those to give sort of a single output, which is what you guess the identity of the person you're seeing is. You could also do things like, in fact, like usually you can compute, in fact, like so a whole probability distribution over outcomes. So you could, in this case, you could compute a probability distribution over identities. So it's like most likely that person is Josh because it kind of looks like Josh, and I know that Josh goes to this university or whatever that I'm on. But it could also be my friend Jan because he also has a beard and is hairy. But it's less likely to be him because he doesn't go to this university. But maybe I know that he's visiting New York, which is where I am, or something. And I could say, it's like, probably 60% Josh, maybe it's like 20% Jan, and so on. So you can compute, that would be like the posterior. So it's like a distribution over outcomes or some variable that you're interested in this case, the identity, which arises from combining a prior over all the different identities plus sensory information that's bearing on the question.
Yeah, so the three main components are that you're combining this prior with the information that you're getting at the moment, which is usually called the likelihood, and then the thing you get from combining that is the posterior, which is like kind of what you now believe. That's kind of the outcome of you doing this little computation in your head.
And the core intuition, though, is right that all of these pieces of information have probability distributions associated with them.
Yeah,
so
exactly.
The prior is not just like a piece of information; it's like a distribution over possibilities.
Yeah.
The likelihood has an associated uncertainty with each piece of data that you get, and then the posterior is now your whole answer, which is not it's the probabilities associated with each outcome.
Yeah, so as Connor said, you could have different kind of strengths of belief associated with several different people after you did this computation. I'm 60% certain that that's Josh and 20% certain that it's Jan.
And it's worth keeping in mind. It's worth keeping in mind that in the sort of psychology and neuroscience literature, that style of experiment is what's going on, but the sort of tasks are very specific things. For example, you might be shown a sequence of oriented bars, like just like a vertical bar and then a bar at 10 degrees to the vertical, so like pointing in like slightly towards the 1 o'clock on a clock position or something like this, and you would see these with pauses in between or something, and we'd be trying to like estimate detection thresholds for like, is it a different bar or is it the same bar that I just saw? So like, what's the resolution at which people can distinguish between these? So the kinds of tasks that psychologists and neuroscientists are interested in tend to be these very sort of simple, contrived but rigorously quantifiable examples.
Yeah,
it would be too messy.
I think is important.
Yeah, it would be too messy to actually do like the campus experiment and see what people think. They have to do it in a very controlled way in a lab.
Yeah. I think maybe I'll just mention this now. It'll come up more naturally when we start talking in more concretely about the papers, I think. But there's kind of another component of this framework, this kind of Bayesian framework for trying to explain human or animal behavior, which is, so far we've talked about combining prior expectations over so outcomes in some, it's very general. It could be like a lot of different situations, but say priors over like identities of people you'll see on a campus in that example, with likelihood, which is the information that you're getting from the data. So in this case, it'd be like sensory information of some kind, to give this posterior distribution. So a updated sort of probabilistic belief about who you're looking at. And another component that comes in then in terms of explaining behavior. So that kind of, this framework in general is going to kind of be able to specify how you could or should combine different pieces of information. But then in a particular task, you have to make, say, decisions, or you have to actually, combining this information has to result in behavior. So you have to move from the posterior, so your kind of your expectations that you've gotten from combining your priors plus data, to doing something. And often in this framework, the way that kind of you're going to get from the information to the behavior is by having some kind of utility function. So some kind of function that describes basically what the animal or person cares about in a particular situation, what they're trying to do. And so the idea is that, animals, humans will be combining their expectations and using their expectations alongside some kind of notion of what they're trying to do to figure out what best to do, given the information that they have and what they want to achieve in vague terms. So there's this notion of like a utility function, which is necessary for defining what we mean really by optimal in a lot of situations.
It's like the goal of what the behavior is for in some way. And also I think it's important to note that when we say like, oh, you see someone on campus and you're not sure who it is, and so you consider who you expect it to be and all that, that's meant to be done automatically. It's not saying that you, every time you make a decision or you kind of receive a perceptual experience, that you're consciously going through these steps. But somewhere in the brain, these things are happening automatically based on your brain's expectations and the information that it's getting.
Actually, just to make the utility function idea, the goal, just more concrete, like to extend our example, maybe when you're on campus and you're sort of looking around, maybe you're, there might be different costs associated with different types of mistakes. So, it might be very much a bad idea to say there's someone that you've had like a terrible fight with or whatever, and you really don't want to bump into them. It might be very bad for you to guess that the person you're seeing is not them when in fact it is, but it might not be as bad to, oh shit, does that example not work?
No, it works. Fuck. It works.
Oh, it does?
Yeah, if you don't want to run into them and there's someone who kind of looks like them, you might as well just kind of, not risk it. Right. If your posterior distribution gives you any, possibility that it's them, you should avoid them if that's your utility function. And so the behavior won't necessarily reflect, the behavior will just be, do you go towards them or away from them? And so in order to map the posterior distribution onto a behavior, you need to kind of know, why am I making this behavior? If I am not willing to risk any possibility of seeing this person, then even if my posterior gives me very low probability that it's them, I'm still going to avoid. So to interpret the behavior, you need to know the utility. Also on like a much higher cognitive level, I remember when I took a class that kind of talked about Bayesian learning and Bayesian theories for cognitive science in undergrad. And after that was the first time I had heard about it. And after that, you can see this everywhere, like kind of in your thinking and in behavior, this idea that you're combining your prior information with, uncertainty about what's happening right now. And so it kind of does appear a lot of places, this framework. And so
it certainly becomes, I think, for people who are well versed in thinking about things in a Bayesian way, it seems like a useful convention for clarifying your thinking about a certain problem. And this is going to come up in this argument. But I mean, if you're trying to figure out like, well, so what was happening in the situation, it just becomes sometimes a useful way of structuring your thought. Like intuitively, well, I had some background information and then I got some noisy data and then I made this decision because I made some inference based on combining those things. And, people obviously, it's an open question empirically whether in a given case people actually combine information in an optimal fashion. It's something that's actively studied and we'll get to. But just the sort of as a useful convention for formalizing certain notions, it can be useful.
I mean, just as a kind of note on that point, right, is that, and this was going to come up, we'll talk about this, is kind of part of one of the criticisms that's made in the first paper, is that when a way of thinking is kind of flexible enough, it can be possible for it to kind of explain anything or something, will be one of the criticisms, right? And I think that's actually, like, we'll go through it in detail, but it's worth, bearing in mind that the fact that something kind of seems intuitively appealing very frequently, it's kind of ambiguous what that says.
Yeah, it's a little risky.
Well, but I think this gets back to the sort of unreasonable effectiveness of math, right? There's a sense in which using probability theory to like understand how things are working, right? There's uncertainty in the world and you can quantify it. I mean, this is essentially what statisticians do. Any way that you can rigorously think about problems involving uncertainty is going to boil down to probability. And I think like Bayesian has a certain connotation, but like clearly the right way to think about uncertain quantities that you want to combine and reason about is in terms of combining their probabilities in the right way. And so on some level, when we're interested in talking about Bayesian modeling, to me, it's largely synonymous with just using, like saying you want to do probabilistic modeling. You want to talk about uncertain quantities and uncertain data, and you want to figure out how to handle that in a coherent way.
Yeah. We're going to get into the details.
Let's get to this first paper at this point. I mean,
sure.
The basic thesis, and we can try to break down some of the points, but the basic thesis is that in psychology and neuroscience, when people try to build models that use a sort of Bayesian framework, let's say, and they'll refer to this sometimes as Bayesian models, and we want to distinguish, so I'll try to use the clear language just from the outset, which is like using, probabilities and Bayesian computation is sort of a framework in the sense that like you specify specific models. Like I think in this specific setting, like looking at a person across the street or looking at a particular oriented bar or something like this, a person is going to, a person or a monkey or an animal or whatever, when they're looking at this kind of stimulus, is going to do a certain kind of thing in order to perceive it. And they're going to combine their sort of background information with the observations they get. And this is sort of just the language in which you specify a specific model. So like saying that you want to do it as a probabilistic model just says there's going to be a probability over the sort of background information they have and a probability that is inherited from the noisiness of their perceptual apparatus, and that they're going to do some combination of that. And there's different levels of assumptions we can make. But the basic thesis of the criticism of this approach is that it's too flexible. You can basically come up with just so stories whereby anything that an organism is doing is optimal under a certain set of assumptions.
I think we should get into optimal.
Optimal too?
An important word that's used a lot. So this first article is setting forth to kind of convince people that all of this Bayesian modeling and stuff, labeling the brain as Bayesian or behavior as Bayesian is kind of overstating the claims. Like there's going beyond what can be said based on the work that's being done. And part of it is that people do these tasks where they then try to kind of use Bayesian math to be able to explain the performance of the animal on the task. And if the performance of the animal kind of is explainable by a Bayesian model, they'll say that the animal is behaving optimally because this Bayesian model says this is what they should do, this is how this information should be combined, and then that's what the animal's doing, and so the animal is being optimal.
Okay, so what does optimal mean even more precisely in this setting, right? So in the formalism, if you make assumptions about what the prior distribution is, so like in some experiment, I guess like, yeah, a good psychophysical experiment that everyone's probably encountered is like a tone test. Like, what kind of frequency can you hear to like check your hearing? I don't know. We did this in school when I was a kid, right? So like you'd hear like tones in a headset, and people would say make some sort of indication when you hear a sound. You might make a false alarm. Like, what if you think that there's going to be like a tone? I mean, I think maybe I was kind of paranoid and did this as a kid. There's like you think like, oh, they're giving me a tone every like few seconds or something like this. So when I don't hear a tone, like maybe you kind of hallucinate a tone or something like this. Uh-huh. This would be because you have like some sort of prior expectation.
You didn't want to let down the tester.
Exactly. Yeah. You think that there's going to be a tone, and then you say, yeah, I think there was a tone because you made, like, you're essentially making up the fact that because you were expecting it. And it may not be like a cognitive thing where like you're trying to like please the experimenter, though that could be a consequence. It could be like an honest psychological thing where like you're kind of expecting to hear a tone. And so since the tones can be very faint, maybe you hallucinate the fact that there actually was a tone. And that would be an example of like a false positive by using a Bayesian kind of model. But so like,
I mean, people like illusions, right?
Illusions are
common.
Also kind of,
People use illusions often to describe this Bayesian idea. So, I don't know.
Yeah, so like, you might see something that isn't there, or you might confound some kinds of things that are in the visual.
So one of the examples that they give in this article is a study that says that if you're looking at something visual, but the contrast is low, so if the contrast is low, it's kind of like weaker, it's harder to see it a bit, and you're looking at something that's moving. If the contrast is low, it appears to be moving slower than it actually is. And the mechanism that was put forth for why this is that when the contrast is low, the information you're getting at that time is weak, and so you're very uncertain about it. So when you're uncertain about the information you're getting at the time, then you rely more on your prior, and if you have a prior that says most things don't move that fast, then you're going to conclude that this is probably moving fairly slowly. So that was an example.
So there you go.
That's a good example. It's worth clarifying that even further, just so there's a very concrete example that we can refer to.
Sure.
I mean, so like, right, the idea is you're looking at things moving on a screen, and you have to estimate the speed of the things moving on the screen. So, in this case,
in the very formal sense, you have a prior over speeds of things on screens.
Exactly.
Yeah.
You have a prior over speeds of things on screens. That's the prior. The likelihood is something about the sensory inputs. And the idea is that in the experiment, the object moving will be darker or bright, or the contrast of the image you're looking at will be higher or lower. And the assumption of the experimentalist is that when you increase the contrast, you reduce the uncertainty in the sensory information. So you make the sensory information like a better source of information.
And so when you then combine them and estimate the
when
speed.
you combine the likelihood and the prior, the relative uncertainties in the likelihood and the prior will determine which source of information you put more weight on.
Yeah.
Right?
Yeah.
So when there's high contrast, you have low uncertainty in the likelihood. You think this is really good sensory information, and I'm going to weight that heavily relative to my prior expectations.
Essentially ignoring the prior if the contrast is
ignoring the prior, right? But when the contrast is low, you think there's a lot of uncertainty here. The sensory input is not that good. I'm going to more heavily rely on my prior. And so the idea is that in the low contrast situation, by looking at people's decisions, you should be able to reveal something about their prior expectations.
And I want to speak one more point about the sort of normative background of this, which is that the math itself, if you make concrete enough assumptions, the math gives you a right answer. It gives you in this case, it gives you the optimal weighting of prior data and sensory information.
Because it is the case that if your sensory information is very noisy, you shouldn't trust it that much. So even if
So there's like a right answer. When we say shouldn't here, we mean that according to the math, right, combining the prior and the likelihood, there's like a right answer.
So this is why
this is
why it's important to explain what optimal means in this sense, because when you say the animal or the person in this study is behaving optimally, it doesn't mean that they're accurate all the time, because they are saying that this movement is slower than it actually is.
So they're wrong, but they're wrong in a way that is like optimal.
Yeah,
According
given
to
the fact that they were
math.
given uncertain information, they are behaving reasonably according to this Bayesian model. So they're saying that they're behaving optimally because they were given uncertain information.
And so, like, to spell out the criticism a little bit more, the assertion that behavior is optimal depends, like we just said, on kind of. So if you have very concrete assumptions, if you set up the model very explicitly, you can compute what the optimal thing to do is. But the optimal thing to do, it follows, right, that the optimal thing to do depends on your assumptions. So concretely, if you have to make an assumption about what the prior is that the animal holds,
and how strong that prior is sometimes,
and how strong that prior is. We can't access this. Okay, so for example, if we assume that animals have a prior that things in general tend to move fast, then when the contrast is low, we'll predict that they will
overestimate the speed of things.
Overestimate the speed of the objects. If we assume that their prior is that things tend to move slowly, then in the exact same experimental setting, when the contrast is low, we'll now be predicting the opposite thing, which is that they'll be underestimating the speed of the object.
And so, like, it's actually plausible. And I mean, in some cases, the way the analyses end up going is something like you sort of optimize the whole setting to explain the data, and
as optimal.
You optimize the whole setting to explain the data as optimal. Yeah. So like you kind of are estimating what the prior must have been to explain the behavior, but then the sort of that sounds like you're doing something that's a fallacy. But I think I'm kind of getting at one of the defenses, which is there's an explanatory power to that, though, right? Like at the end of the day, you could say like one explanation for why or at least it feels like there's an explanatory power. One explanation for why the guy seems to be underestimating the speed when there's low contrast is because he had a prior that was saying that things don't move. And that becomes part of the explanation itself. It's like you explored the different possibilities of what kinds of models could have explained that behavior, but the sort of outcome was what the model was that was able to describe the behavior is itself the conclusion. But that is definitionally a just so story in some sense, right? It's like at the end of the day, retrospectively, without making subsequent predictions, you can explain a certain finding. Any behavior can be explained in terms of some sort of probabilistic model. And I guess that's basically the criticism in spirit.
Yeah, so if you don't have any other reason, aside from this experiment you did with low contrast moving stimuli, to believe that your subjects have a prior that favors low moving stimuli, that suggests that most things move slowly, you're just making that up so that your model will fit the data. And so to then kind of sell that as, oh, look, these subjects perform optimally in this motion estimation task, it doesn't seem like you're being fully honest. If you phrase it as
a disclaimer, we're not picking on any particular paper. We're kind of giving a cartoon version of what one of these psychological findings could be sold as.
And this is kind of just part of what this initial article was complaining about in a way, is that it's not fair, or it's not even necessary or interesting to say that people are behaving optimally in these settings. Because what you're really saying is, I found a model that explains their behavior. And that's it. And so the interesting thing is, well, what are the properties of that model, and what does it tell us about cognition? The fact that the model and the data match, that's just what you set out to do, was to find a model that matches the data.
I mean, maybe this is jumping slightly ahead. A kind of takeaway feeling I had from reading these papers is that, I mean, we'll have to get on to kind of what's the alternative to this Bayesian approach that, maybe the people writing this paper kind of might advocate or suggest at least. But I come away with this impression that in a way, we're studying kind of very complicated subjects. I mean, say animals or human beings that can do a lot of things. and we're trying to explain a very limited set of behaviors, usually like very contrived behaviors where we're kind of assuming away a lot of things that are probably contributing, like the history of the animal or all of the other things that they can do and so on. So, I mean, to me, it ends up feeling like this debate over what the right framework is kind of largely arising out of a sort of unconstrainedness of what we can so far study relative to what we would like to be able to explain in a way. I mean, we're trying to say, oh, people are doing sort of optimal Bayesian things, but it's, it is such a hugely flexible framework that people might be optimized for some very specific kind of huge kind of array of interacting types of tasks, and they might be able to change over time and so forth. So, but I think that this can somehow apply to sort of any current theory of cognition or behavior. I mean, there's just like
I want to jump the gun a little bit. So I think we should concretely lay out some more about what the criticisms are concretely, but at the same time, I think in the background, and I mean, maybe I'm projecting too much, but to me, there's some elegance that motivates the use of like Bayesian framework beyond like actually making the concrete claims. So like, if it's the case that you look at some behavior and you think, I want to build a model of that, if you want that model to be probabilistic, essentially the kind of modeling framework you're going to use is going to kind of overlap or basically be what people refer to as Bayesian modeling. You're going to say, here's this behavior. I want to explain it in terms of a probabilistic model. That means you're in the Bayesian camp, basically by default. And like there's an intellectual aesthetic sort of elegance to the Bayesian framework that allows you to separate out conceptually different pieces of information in a useful way and compute rather hard quantities in a sort of known optimal way, at least approximately, right? Like we know if you specify the prior and you specify the likelihood, we know how to do the computation, at least approximately, for like kind of a very wide range of problems. And at this, and moreover, like these tools are sort of clear. So like they're not just like they sort of allow you to express these things, but they're also like scientifically accessible in that the knowledge is separated out in a certain way. So like while things like neural networks are being very, very widely used and are useful in like data science settings where you want something that can predict something well, like from a scientific standpoint, if you want to have like a clear separation between different causes that combine in a certain way, like the probabilistic inference framework or like using Bayesian probabilistic inference is a very kind of rigorous and yet at the same time clear way of computing rather complicated quantities, certainly for the scale that's used in these kinds of settings.
I think it can be hard to appreciate if you haven't tried to do science, these kind of modeling motivations that you're talking about. But
it's like the question, in the background is like, what questions is it interesting to make or useful to make about a behavior? If you're observing some behavior and you want to characterize it as a scientist, the like what seems natural to I think many people is to like build a model that explains why that behavior arose. And you're gonna look at the behavior and you're gonna try to come up with some math or some theoretical framework which explains where that behavior came from. And once you know where that behavior came from, you can make predictions about what other behavioral consequences will follow. And there are many frameworks you could probably use. So like this gets back at this question, like what other frameworks are there? You could use like a neural network, for example, to explain the behavior.
Right.
But it becomes a question then, what kinds of predictions can you make?
And like I think the Bayesian, this is another one of the defenses, like the Bayesian framework does have a certain clarity to it. I mean, I think coming back to the speed estimation problem is useful here. So in the first paper, the critical paper, the paper critical of the Bayesian modeling kind of approach, at the last part of the section where they talk about this first paper about speed estimation, they sort of talk about this idea that the prior is not, they don't check if the prior is kind of reasonable, quote unquote. So, but this is a very concrete type of prediction that these models actually make. So you fit the behavior, and part of the way you fit your model, like you adjust the parameters of your Bayesian model to explain the behavior. Part of doing that is adjusting the parameters of the prior. But once you've done that, you are actually making a prediction about the kind of priors that the animals have. It's very difficult to access the priors that animals have. It will be it's hard to know how to do that. I mean, you can do more behavioral experiments.
So if you did different experiments that also required a shared prior, then
that includes some of the information.
If two experiments that you did, if you did two experiments that had different behaviors that you thought relied on a shared prior, and they gave different estimates about what the parameters of the prior are,
that would be contradictory.
And you would say, well, that wasn't a very good explanation.
Yeah. Another thing that you can do is you can kind of make this other assumption, which is that presumably if animals have priors over certain types of quantities, it probably should be related to what you see in the world. And so, for example, if you predict, as they do in this case, that animals have a prior to perceive things as moving slowly. I mean, it's not. There's ways that this might not necessarily be the prediction, but naively, the prediction is things have a bias towards moving more slowly in the real world, right? And a lot of people do this. So he's criticizing the authors of this paper for not measuring the distribution of speeds of moving objects in the world. But there is a lot of people who do this kind of Bayesian work, Bayesian kind of psychological or neuroscientific work. They
look at
do
the natural statistics distributions of various stimuli. So the
question would be is it reasonable to have a prior that objects move slowly?
Yeah. And if you go and measure, if you're talking about humans in a city, maybe they see a distribution of things that move faster than people who live somewhere else. But if you live, on a rural college campus or something like this, you might...
Yeah, where everyone's just moseying around, drinking
That
tea.
wasn't what I was thinking. I was just thinking there aren't, cars, flittering by all the time. But.
Right.
I mean, certainly when you're looking out at nature, you will see occasional rapid movements, like a bird flying by or something like this. But most of what you're looking at is static. And so it becomes complicated, right? Focal things.
But that's the point, is that it's hard to get at these things.
Yeah.
So, maybe the only thing you can do is to give behavioral tests and see if they all give you the same estimate of what the prior is.
Yeah.
But we should kind of carry on with what the arguments against this are.
Grace, why don't you more concretely summarize the whole?
Yeah. So as we said, they complain that you can build these models in any way you like and then therefore get a model whereby the animal's behavior was optimal. And you can do that by, as we said, kind of just deciding what the prior is or fitting the prior to the data, which they consider, a just so story. You can also play with the utility function, which, as we said, kind of describes the goal of the behavior and is a way of mapping the posterior to behavior. And the example they give for that is it was observed that goalies in soccer or football, depending on what continent you're on. They actually just what country. Anyways, in this sport, when people have penalty kicks, the goalies have a habit of kind of anticipating which direction the person will kick in before they even start to do it. So they're kind of just making a guess and go all out in one direction. Whereas if they just waited to actually see where the person, wait until you actually see the ball start to move and then go, they have a better chance of actually blocking the goal. And so it seems like they're doing something that's irrational. And a way that you can, in a Bayesian framework, explain why they're doing this is to say that their goal isn't actually to block the most balls necessarily, but as part of their utility function, they have a desire to appear like they're trying really hard. And so then if they move very quickly and go all out in one direction, then it's clear that they were giving it a go. Whereas if they tried to wait to see where it goes and then are too slow to respond, it seems like maybe they were being lazy. So if you change what kind of the goal of being a goalie is, then you can explain this behavior. So this is something that they considered a little ridiculous in this original article. Then they also make the point that it's unclear if these theories can be falsified. So how would you prove the people doing this modeling wrong in any way? And they also complained that these Bayesian models and their ability to fit behavioral data aren't usually compared to other models to say that the Bayesian model actually is better at fitting the data than a non-Bayesian model would be for the same data. And I think these points kind of, to expand on the second 2 points, we should talk about the different types of Bayesian neuroscientists that they list, just because we've been talking mostly about just using Bayesian math to model behavioral data, but there's actually kind of different layers to what people use this Bayesian math for, or what they are saying when they say that the brain is Bayesian or something like that.
Mm-hmm.
So the 3 categories that they give are extreme Bayesian neuroscientists, who they say...
Which, I mean, like, yeah.
Extreme radical Bayesian neuroscience.
There's a little bit of an over-categorization going on here, but fine. Yeah.
But, like, fine. These are the categories that they want to use in this paper.
Yeah. So they say extreme, which I think they say, like, these people don't really exist, or there's very few of them, but, I mean, that's why they're the extreme. And they say that these are people who say you can only understand the brain at a descriptive level. Like, the only thing we can do is explain behavior via these kind of high-level mathematical models, and to try to, like, know what the brain is doing deeper than that is, a fool's errand, I suppose.
A fool's errand.
All of neuroscience is a fool's... No, that was not a direct quote. The next category...
I want to write that in a paper, like like in the discussion section. Such and such a branch of neuroscience consists of fool's errands solely. Yeah. Awesome.
The next category is methodological, and that is people who say that these Bayesian models are just a way to describe behavior, and that's useful. It's useful to have a framework and mathematical equations that can tell us how animals are behaving in different circumstances, and this can constrain any other models that we want to build about how the brain works, because they have to still produce behavior that fits in with this model. And then the third category is theoretical Bayesian neuroscientists, who say that Bayesian behavior is inconsistent with non-Bayesian heuristics. So what they mean there is that if we observe that the behavior can be fit by these Bayesian models, then that kind of means that the brain itself is implementing the Bayesian math that we use to describe these models. Whereas you could imagine that there are kind of ways to get the same outputs, even if the brain is not in some way implementing this math that we use to produce those outputs. And so they'd be using heuristics of some kind that in the domains that we've tested still look Bayesian, but they're not actually, like, the brain itself isn't representing these different distributions and combining them in the way that we do when we calculate posteriors and that kind of thing.
This seems very confused to me.
Yeah, so I agree. So I think we should summarize the last 2 major points of the paper real quick, maybe.
Yeah, sorry.
So given that they talk about can these theories be falsified, and I don't know that I fully understood their argument about why these particular, like, why Bayesian models more than anything else couldn't be falsified. It seemed like they were saying that they don't make as many predictions as some other models, but I think that they were comparing these Bayesian level, or these Bayesian descriptions of behavior to more mechanistic models of what, like, actual neurons and brain areas are doing. And so if you are going to put forth what you think the actual mechanism behind the behavior is, then you're going to probably get some more precise, situations where different mechanisms will lead to different outputs. If you're putting forth a high-level theory that's just meant to describe the behavior and not explain how it comes from the brain in a mechanistic way, then you won't have as precise of predictions for the future. But that's not a thing that's particular to Bayesian models. That's just behavioral modeling generally.
It's the level of the modeling.
Yeah.
It's like, if you're not doing neural modeling, then you're not going to make predictions about neurons.
I mean, so I think we're all coming at this from a perspective of we think that a lot of these critiques are confused. I have some things to say in defense of it, but I think we should finish summarizing the major points. So basically, some other major points are how that, like, if you're talking about this mechanistic version of it, where, like, the brain is supposed to actually implement Bayesian computations, there isn't much empirical evidence in the scientific literature for that. So that's another kind of point that's made. And then they have another subsection on conceptual problems with the Bayesian approach to studying the mind and brain, which I think is sort of their miscellaneous category, where they throw in all their other perspectives on why this isn't working. But I think at a high level, they are missing. I think there's legitimate concern, and then these people tried to form a full criticism of Bayesian methods, but it doesn't seem like these authors fully get what's going on with. So the legitimate concern, and I think it's basically there are overstatements in the literature, as far as I can tell, on the scope of what Bayesian modeling is actually telling you.
Yeah, this is definitely true.
Clearly true. Yeah. And
that comes back in the response to the response.
It does, yeah. And people will talk about optimality kind of without grounding it. And a lot of this just feels, though, like the way scientists tend to oversell the conclusions that they have.
I don't know. I think because it's not there, it's almost that the statement is the opposite of what the science was. If you title your paper, "Humans are optimal in such and such," that is not the finding of your work.
Yeah, I object to that.
Yeah, the finding of your work is humans have a prior that favors slow motion or whatever it is.
Completely
and so it doesn't, because usually when normal scientific overstatement is just kind of going a step beyond in the direction of your work. This feels like they flipped the direction of the work.
I agree. So it does seem to me that there is something poorly conceived of the way findings related to Bayesian modeling are advertised or promoted, right? And I think maybe we all agree on that outright.
Yeah, I think I agree.
But at a deeper level, using, again, the sort of Bayesian calculation system to make probabilistic models and compute quantities about probabilistic models seems like a reasonable thing to do. It seems well-founded, and it doesn't really seem in conflict with a lot of the other things that go on. It seems mostly about how it's presented. So, if you want to say, are there non-Bayesian models that explain something, this just kind of gets at the notion, okay, there's implementation details, and right. So, and this is not to dismiss everything as implementation details, but it's whichever one comes out first is fine. If you find some non-Bayesian modeling, which an example would be using a neural network to do something, right, is non-Bayesian generally. So I'm going to have a neural network that can predict a certain quantity that matches with a human's behavior or something like this in a certain task. You would say, well, that's a non-Bayesian approach that explains the behavior. So my alternative to the Bayesian approach is that a neural network-based approach explains human behavior better than a Bayesian approach. It's this comparison seems totally artificial. In reality, you could interpret the computation performed by the neural network as something that's kind of approximating a Bayesian approach.
Yeah, because what if someone just gave me, someone just gave me that neural network and said, describe what it's doing, I would say, well, it seems to match a Bayesian model. I can make a Bayesian model that will describe what this neural network is doing. If they can both explain the behavior equally well, then you could probably do that.
Right. There's a funny thing here where what we're saying kind of sounds like a criticism of the Bayesian thing, right? Which I think it kind of lies at, I think, part of the heart of at least part of the confusion or the conflict.
Yeah.
Which is that, it's I think maybe the framework versus model distinction is very relevant here. Yeah. So you can't, and they talk about this in the response to the first paper talks about this. You can't falsify. So the claim is things are not falsifiable because of what we're talking about. You can often interpret whatever behavior as Bayesian in some sense by manipulating things correctly, right? So that seems like a criticism. So it's not falsifiable. But the point is, you can't falsify you do not falsify an entire framework.
Yeah.
You have to posit
if we thought about
specific models.
Exactly.
And then you can attempt to show whether or not those models are useful.
Think about it just even more broadly with math.
Yeah, right. You can't falsify the use of mathematics in science.
Yeah.
It's just a meaningless statement.
It's oh, well, I had a model, the model that I'm talking about is that this thing happens for some qualitative reason that I'm only going to describe in words. And if you try to put a mathematical model to it, and my verbal description has better predictions for some reason that it seemed hard to imagine, then the math, the use of math is falsified. No, it just means that the particular math that you used was not correct, but it doesn't mean
now,
that, the whole endeavor of trying to mathematize it is...
There is a subtlety, right, of course, which is that because it's human beings who are actually doing the modeling, we are like flawed social creatures, okay, who, for example, like we already said, are trying to, get grants and impress other people and so on and oversell things. It can be that like this nice, clean, theoretical kind of distinction that we're talking about, saying, well, this is a framework, I posit a specific model, I draw certain conclusions from that model, I make predictions, kind of iterate the process and so on. It doesn't always work that cleanly in practice. Of course, for example, right, you make the statement like Grace was saying, I did this Bayesian thing, and then you make a statement like, which shows that humans are optimal. In making that statement about optimality without kind of the relevant sort of, without the details, you're actually kind of buying into the framework picture, I think. You're kind of saying the Bayesian framework has been shown to be like correct, which I think is the flip side of the erroneous argument that you can't falsify the framework.
Yes.
So you also shouldn't sort of...
The framework can neither be correct nor incorrect. The Bayesian framework is not true or false. It's just like an approach to formulate specific models.
And a specific model can be true or false insofar as it describes the behavior well or not.
Yeah. Okay, so I mean, we've summarized some of the major criticisms and actually gotten at a lot of the responses. Are there any sort of core responses that we didn't address that we think are relevant to mention?
Yeah, I mean, I think the people who wrote the response, Griffiths, Charter, Norris, and Puget, are people who were kind of cited in the original article, and so naturally they they had a desire to defend themselves. And I mean, interestingly, a lot of the responses along the lines of like, basically they just don't think that they were characterized correctly. It's not the case that they disagree with the criticisms, they just don't think that the criticisms are true. They're not accurately capturing the work that they've done. For example, we talked about these 3 different levels of Bayesian neuroscientists, and the methodological one is the one that just says that this framework is a useful way to describe behavior, and then we can use that description of behavior in future work. They claim that that's kind of the only one that exists, and the people who claim that the brain actually has to be implementing the type of math that we use in Bayesian modeling, that they don't feel like anyone really stands by that claim. And so it lends itself to kind of a more moderate description of what Bayesian modeling in neuroscience is about. If they're just saying that it's useful as a way to describe behavior, that's kind of a statement that most people can agree on.
I mean, an effect of choosing a certain framework to work in is that, it shapes the way you think about things, and it shapes what kinds of questions you're going to ask and what kinds of answers you're going to look for. And I think, I don't know, I guess I don't have a very sophisticated, in my own mind, kind of attitude to the question of, is this Bayesian way of thinking net, like taking into account all of the sort of strange interactions that go on, like between a scientist's work and future work and the way you think and what you do and so on. Is it in some way harmful? I mean,
yeah. So of course, like, the weakness would be like Bayesians care a lot about prior knowledge and uncertainty, and so they do lots of experiments that might be informative for that kind of thing. But maybe if you don't care about those things, it's like those experiments are really not informative. So there's like, by a certain, from a certain perspective that doesn't care about these kinds of things, all of the experiments that these Bayesian psychologists are doing are essentially uninformative, because they're telling you about quantities that aren't particularly interesting unless you're coming at it from the Bayesian framework. So I mean, I think there's definitely a real risk in terms of what priorities get shaped by this. And I think, this is all pre the somewhat recent return of neural networks, and I think that there is, a little bit, a vague amount of disconnect between the people who study like neural networks and the people who are super Bayesian, at least in certain ways, because, neural networks are less elegant.
Kind of conceptually or
clear,
somehow.
Yeah. It's harder to interpret what neural networks are doing than it is to interpret what a Bayesian model is doing. The fact that people prioritized explanatory simplicity, like, or comprehensibility of the model itself, presumably biases what kind of explanations they're willing to tolerate.
Yeah, and
Right.
so one of the points that they make in the response to the original article is that these models are trying to offer a why instead of a how. Like, why is behavior the way it is? Let's figure out what the animal is trying to optimize by fitting a model to it, and then we can interpret that model and say, well, clearly, humans have these kinds of assumptions, and they're combining it with information in order to achieve this kind of goal, and I can infer all those things by building this model and fitting it to data. And so this again speaks to the idea that they're not trying to say how the brain is actually implementing these things, and the brain could be implementing things in any different way as long as it leads to the same behavior. But then they ask this kind of interesting question. They kind of like pose this question to the authors of the original article that, is cognitive science done as soon as we know the neural and cognitive mechanisms behind things? And they would say that it wouldn't be done even if you can
build a robot that does the same thing.
Yeah, even if you build a robot that has the same behavior, you're still not answering why humans had that behavior in the first place. And they're saying that these models can answer that. And I don't know how I feel about that.
I'm not very sympathetic to that argument.
Yeah. Because I think that it is the case that even within a Bayesian framework, there's a lot of different ways to get the same behavior. So you could build many different Bayesian models that will produce the same behavior. And so can you get at a why, or can you get, I guess, at a set of different possible answers to the why question?
I think that there's a little bit of, I don't totally buy their parsing of the why-how distinction. But I think that I'm reluctant to allow for a sort of, I don't want to use mystical because no scientist is going to, is going to accept that as anything other than a slight. But if you lump a sort of ambiguously large number of questions into things that are like somehow still questions, even if you know how to mechanistically re-implement something. So like if you can build a model of a person, like a robot that acts just like a person, I don't really believe there's a sort of ambiguously large space of questions that are still interesting to answer about the way that agent behaves, that person or that robot behaves. Like, there are things that you might want to understand about it, but it's not clear to me that those are like deep why questions, or that those are somehow like of an arbitrarily large space that like should still exist. It's like there is an infinite set of questions you can ask about anything. Like for any human behavior, you can there just are like sort of combinatorially an infinite set of questions you can ask, but that does not make them all worthwhile or interesting. While when we're so far from understanding how the brain does work, it does seem worth restraining people's scope to the questions that like a lot of people can agree on as being like quite relevant to the advancement of like the sort of figuring out how the brain does work, and not some amorphous space of like what are the reasons why the brain works the way that it does.
One concern that I do have about this kind of Bayesian thing, and this is a concern very much not on the level of doing one study, especially if you're very clear about your conclusions and you don't kind of commit these kind of probably socially motivated fallacies of like very much overstating your conclusions and so forth. A concern I have is, especially when it comes to the social sciences, right? Oftentimes we're studying extremely reduced situations, okay? So we're studying like, make human beings making very, very simple decisions. And we can use a framework, say that's like a Bayesian framework or something, and we can make good concrete models in that framework. And those models can be great, like by all these kind of usual scientific measures of like they have clarity, they can be falsified, right? They make predictions, whatever. But then there's kind of this disconnect between that rather humble work, rather very concrete, quite humble, and I'm not saying there is, but there's a potential disconnect between that and then these kind of somewhat grandiose sounding conclusions about like that almost are conclusions about kind of human nature or something. Like people are this type of optimal, that type of optimal. This is definitely not inherent to the approach. It's just it's a kind of
because it does it seems like. So I'm totally in support of the idea that, it's good to have accurate models that describe behavior, accurate descriptions of behavior. And to have accurate descriptions of behavior, you probably need to make a mathematical model.
And
that
those
does
mathematical models probably have to include probabilities.
Yeah. And
Right,
so
yeah.
the Bayesian framework seems well suited for this. But the question is then, what do you do with those descriptions of behavior? And to me, I would say, okay, well, now I want to build a neural circuit that can also produce that behavior so that I can understand how the brain leads to that behavior. For this field, there is the risk that they're just collecting these descriptions. They're just showing all the different ways in which you can describe behavior in a Bayesian way, and I don't know what the sum total of that is supposed to mean.
Yeah, and I think, to be honest, I mean, this maybe sounds conspiratorial, but like on the level of looking at a whole literature or something, they're kind of like emergent themes that happen, that kind of emerge, right? Sort of like notions of. This is not so. This isn't really about the debate between like Bayesian approaches versus other modeling approaches. You could probably come up with similar criticisms of other frameworks, depending on what those frameworks were. But there's just, I mean, this is like a general thing about like neuroscience and psychology that kind of bugs me generally, which is a lack of care in describing how limited what you're doing is, and a kind of a certain level of willingness to not either be silent in terms of cautionary tales, like not saying, oh, well, let's not jump to any conclusions, right? This doesn't mean anything particularly strong about real human behavior in like very complex situations and so on. That would be kind of a silence, which I think we should criticize. And the other thing would be like people who are kind of almost, I mean, we know these characters. There are these characters, there are bullish people. And there are these characters like who are famous. I'm not going to name people, but like who go around writing books about like, oh, this is how human beings are. And it's just kind of like, give me a break. I mean, sometimes you can state rather simple things that have been potentially, have been somewhat overlooked, or can't, like some simple but useful conclusions about human behavior that you can glean from like a whole psychological literature, and that's very valuable. But I don't know, somehow a lack of caution and sort of clarity about what is the level on which we're studying human behavior, and really how much can that relate to real human behavior or social behavior, these kind of things. Yeah. I mean, my point is just that, like, in some way you could be paranoid that the Bayesian thing makes people sound like kind of like this Homo economicus type of thing, or some more subtle version of that. This kind of, I don't know, whatever. This is a concern that I have often when I read these kinds of things. More in the decision-making context than in like perceptual, obviously, because like it doesn't really matter if our retina is Bayesian. It doesn't really say that much about like the economic behavior. Anyway, that was a bit of a rant. Oh.
Yeah, it is important to note, I guess, that these models are used to describe both perceptual computations as well as decision-making and memory and forgetting, and everywhere all across the brain. Separate Bayesian models are used to explain. Okay, any parting thoughts?
I don't know. A caution with respect to letting enter into the world a notion of human beings as like super rational and optimized.
Sure, yeah.
And like neuroeconomics. I mean, this is a thing now, And it's like, you study someone doing some like ridiculous task in some lab, right? Or some little game that they're playing with other people. And you say, oh, the psychologists have shown and told us that in fact, these kinds of things these are the kinds of decision-making rules that people use, and we'll just like plug that into our model, and now our model is like A-okay, and we can proceed. Like, I don't know, that shit is ridiculous. Anyway.
It does seem to me that like while there are concerns about using a Bayesian modeling framework, and I would say valid criticisms of the literature, the criticisms really should be more about what you can make statements about, not about the utility or legitimacy of the approach. Right? Yeah. I mean, it's kind of clear that like Bayesian framework for like formulating models is consistent. I mean, it's a mathematically derivable set of statements that you use to compute things.
Yep.
It's like the real concerns have to be about how interesting and useful the kinds of conclusions you get from this field are.
I agree.
And I think there are some interesting things to be learned. I think we don't want the statements to be like overzealous in terms of what they're promoting, but you are formulating, in some cases, very clear models about, at least conceptually, what's like the models are almost at the conceptual level, but they can be very clear. And so I do think that there's a utility in that. I don't think that they necessarily get into mechanism. And, it's not clear if they're like sort of useful from an engineering standpoint in terms of engineering cognition. But they are useful, I think, for helping to organize how scientists think about the classes of problems that organisms face.
I think it's always a good idea to critique a prominent tendency in thought in a scientific domain, like always, because you're just sort of saying, okay, fine, we're doing this kind of thing. Maybe there are other kinds of ideas that we're like ignoring because we're so focused on this way of thinking about it. I mean, that's one thing.
And it results in interesting conversations like this where people have I mean the papers, right? I mean, it's not so often that scientists step out of their like tendency of just doing the work that they're good at and actually engaging with people who don't even agree that style of work is super worthwhile. It's nice for those conversations to be had so that
that's very
both
good.
sides can have at least a bit of an understanding of what's going on.
So yeah, this exercise of having these articles like actually in print and back and forth arguing about this topic, I think is just like a really nice thing to be able to read, because this is something that a lot of people pursue, this Bayesian modeling, and it is important to have open discussions about what its goals should be. And it's nice to see prominent scientists in the field openly discuss these things.
I agree. Yeah.
Yeah.
All right. See you next time. Hey, if you're still listening to this, you must really like us. So how about you go to iTunes or Stitcher and rate the podcast, give us some feedback. You can also go to our website, unsupervisedthinkingpodcast.blogspot.com. You can comment on different episodes, or you could give us ideas for new topics you want to hear about. We would love to hear from you. Thanks.